Okay, so we're going to be talking about parametric curves. And this is the beginning of multivariable calculus. This is what these last sections of the course are actually doing. They're an introduction to multivariable calculus for you. So far in calculus, we've been considering functions from the real numbers to the real numbers. And maybe from some interval, or maybe from the entire real line. But it's always been from real numbers to real numbers, right? And you people at this point are very familiar with this. We can represent these things as graphs like this. We've learned about these things to quite a solid degree. But there are many things in the world that we cannot represent well with a function from R to R. Okay? There are many things we'd like to describe. There are many physical laws which we'd like to express in the language of maths, and we can't do that simply talking about functions from R to R. Yeah? So ultimately where this goes to is that we can develop a calculus for functions from Rn to Rm. Okay? So multivariable calculus is nothing but calculus for functions from some subset of Rn, n-dimensional space, into Rm, where m could be equal to n or could be anything else. Yeah? And there is a powerful theory of being able to do calculus for these functions. And it's a subject I hope you all study, because this is an even more powerful subject than single variable calculus, as you might expect. And it's got much more applications to other sciences and engineering. Okay. And what we're doing now is we're starting to reduce this with this topic, which is the easiest way, the easiest step out from the world of calculus from R to R. And what we're going to be doing here is doing calculus from R into R2. Okay? That's what parametric curves are. So these are curves which we're going to parameterize by x of t, y of t. So it's a good idea to think of t, at least for the time being, as being time. Then for every moment in time, there exists some x of t, y of t, which is some point on the plane, right? So we can just put its coordinates, right? So this will be the x, this will be the y, so this will be x of t, y of t, okay? And as t changes, this point changes, right? So as t changes, the point is moving around, right? So ultimately, it will trace some kind of a shape, right? Maybe like this. Yeah? Maybe we start here at some start point, x of a, y of a, and we end up here at some endpoint, x of b, y of b. And for every t between a and b, it's some point along this curve. Okay? And if you think about what we've really done there, we have got a function from t, which is the real numbers, into x of t, y of t, into the points on the plane R2. So it's a mapping into R2. So it's the simplest version of a function in multivariable calculus, where we go from dimension 1 to dimension 2. Yeah? So in this case, n is equal to 1, m is equal to 2. Yeah? And this is a very useful thing to be able to do, because there are many curves that we would like to understand that come up naturally, and other problems that we can't describe as graphs. Right? This thing cannot be described as a graph of a function. Right? Because a graph of a function is something where for every x there exists one f of x, and it's well defined. That's not true here, right? Because there are multiple points above this x. So we cannot describe this as a graph of a function. Yeah, we can do it locally if we try hard, but we can't do this globally. So we'd like to be able to deal with this thing as an object by itself. We'd like to be able to work with this thing that goes from t to x of t, y of t as an object in itself, and do calculus on it and understand it in an analogous way to how much we understand functions from R to R. Okay, that's what we're about to start to do. That's what these coming sections are about. We're going to learn about parametric curves, later polar curves, which are an example of parametric curves. Yeah? And if you, as I hope you all do, study multivariable calculus, then you'll do this in a more general framework and you will learn many more things. But the point of this, again, is to somewhat introduce this topic. Okay, cool. So the best thing to do is to start with some examples. So here is the first example, example 1. Sketch and identify the curve given by x of t is given by t squared minus 2, and y of t is given by t plus 1. Okay, so a metaphor I like to use to describe this is to think about the motion of a bee. Okay, so a bee will move in the plane, right? And every point in time, the bee's position on the plane is given by x of t, y of t. So you can think of a parametric curve as describing the motion of a bee with respect to time. Yeah, so here it is at time 1. If this is, say, t1, let me start it again. Here is at time a. If this is t1, this point here can be x of t1, y of t1 right here. Let's call this t2. This is where it is, right? This could be where it is at x of t3, y of t3, and so on, right? And ultimately it ends up here, yeah? And the way I've drawn it is just gone around like this. It doesn't actually have to go around like this. It can actually go around, and then at a certain point it can backtrack on its own path and go backwards, and then stop again, and then go forwards again, right? Yeah? Yeah? So there's two separate things. There's the set of points that the bee goes over, and there's the actual path of the bee. So we can have the same set of points that the bee goes over, but there will be multiple ways that it sketches out this set of points. Yeah, we'll see that in more detail later. Yeah, so don't make this identification of the set of points I'm drawing here with the parametrization in the sense that there's a one-to-one correspondence. That's not the case. In this case, when we do functions from R to R, that is true. Once we draw this graph, then there's one function that produces this graph. Once I draw a curve, there are multiple different parameterized curves that will give this set of points. Yeah? And we'll see that. We'll see that coming in a second. Okay, so here we have some explicitly given parametric curve. Okay, and it's not telling us what range of t, so we're going to say this is from all possible t, from minus infinity to infinity. And it wants us to sketch and identify this curve. Okay, so sketching this curve is something that you're going to have to build a mental muscle to do, because it'll probably be new for most of you. But if you remember how you learned to sketch curves from R to R, it was like a slow process. When you first started, you had to like put points in and put them all together. But as you got better, you could just look at a function and see what it looks like, right? The same is going to happen as you work on these kind of things. Your brain is going to pick up and start to see what these things look like as you continue to work on them. So let's think about it. What does the y do? Well, the y coordinate with respect to time is moving just in a very straightforward way. It's just moving upwards, right? So the y coordinate, so this is the action of the bee. The y coordinate is just increasing, right? In a steady way. Yeah. So if we ignore everything else about the bee except its y coordinate, then it's just steadily rising. Yeah. But the x coordinate is doing something more subtle. It's a quadratic behavior, right? So when t is equal to 0, for example, the x coordinate is 0. Yeah. But then as t increases, then this thing will be bigger than this thing for small t. So it starts by it's going in this direction, it's negative. And then as t gradually increases, then this guy will dominate, so it'll start to increase and go in that direction. Yeah? So if you ignore the y-coordinate, just think about the t-coordinate. The t-coordinate is behaving in a quadratic way, right? So we start at t equals 0, goes backwards, and then starts going forwards faster and faster and faster and faster. Yeah? Yeah? You see what I mean? Yeah? So we're going to try and put those things together. So the y-coordinate's going upwards in a steady rate, and the x-coordinate is a quadratic. It's behaving in a quadratic way. So what's that going to look like? It's going to look, so watch my finger and notice how the y-coordinate is going to change steadily, and the x-coordinate is going to behave like a quadratic, right? So it's going to go like this. Yeah? It's going to go like this. That's what we expect. That's what our intuition tells us if we try and put these informations together. Yeah? All right. But we can now do some algebra to actually see what this thing looks like more precisely, because it has a very convenient form that y is just related to t in this very simple way. So, solution. I almost did a parametric curve on the L there. Solution. We can solve t in terms of y, right? So t is equal to y minus 1. And then with this t, we can put it into this thing right here, and then we'll have x as a function of y. So put this into star. And we're going to have that x is equal to y minus 1 squared minus 2 y minus 1, like this. And then we can expand that out. So we're going to have y squared minus 2y plus 1, and then minus 2 of y minus 2, right? So we're running out of space. Let's put it down here. So what's that? We're going to have this minus 4y and then a plus 3. So this is going to be a y squared minus 4y and then plus 3. And sure enough, that's a quadratic, right? It's a quadratic. So we have x, if we think of it now as a function of y, is a quadratic, right? So we're thinking about x, the function is a function, we're thinking about the function as on the y-axis now, depending on the y variable. We have that x is, as a function of y, looks like this, which is indeed a quadratic. In fact, it's a quadratic we can factorize. So this will be y minus 1, y minus 3, right? Cool. So it's going to cross here at 1, and it's going to cross here at 3. It'll be negative. It'll be negative like this. And then it'll grow like this. And then it'll grow like this. Yeah? So that is kind of like the thing that we were thinking it was when we just tried to visualize it, knowing that the y was increasing in a steady way and the x was going like a quadratic. Yeah? This is a new topic for many of you, and it will take some. If this is completely new, this will take you a bit to actually start to feel comfortable with this. But it isn't actually hard. This isn't actually hard so far. Yeah, it's just new. Yeah. Cool. So at time 0, where is this? Where is this? Where is that? Where is? Imagine this is a b. At time 0, where is the b? Where is the b at time 0? Just look at the equations. Time 0 is t equals 0. So when t equals 0, where is the b? No. No. It is 0, 1, right? So the question where means where on the xy plane, right? Because that's where the b lives and is moving, yeah? And when time is equal to 0, then we put 0 into this, and we find the x-coordinate 0, and the y-coordinate is just 1. So at time 0, this is where the b is. So x of 0, y of 0 is where it is at time 0. Cool. All right. At time 1, where is the b? Yeah, but 1, 2, which will be like around here, I guess, right? Yeah. Cool. All right. Yeah. So the just as analogous to when in Calc 1 you were first learning about how to sketch graphs, probably you learned by just taking points like this and just saying, okay, when x is equal to whatever x1, then I find that f of x1 is whatever this value, so I'll put this here on the graph, yeah? And when x equals x2, then f of x2 is here, and then you would just connect up the dots, right? So back in middle school, presumably, that's where you learned first about graphs and how to sketch them, yeah? Yeah. And for these kind of questions, when you start at the very beginning, you probably will be served by doing something similar. If you don't see anything else going on, or even if you do but you're not sure, just stick in values into your parametric curves, put them on the xy plane, yeah, and then connect them up. And that's a crude way to start to do the graph, yeah. And you might have to do that, or you might do things like this and then just check that it makes sense with what happens when you stick in particular values. Yeah? But this is an accessible thing. I mean, this isn't morally any different than sketching this thing, except that we have a function from R into R2. Right? All right. I'm going to raise the board. Do we have any questions before I do that? Everybody okay? Yeah. As always, everything builds on itself. So if you're unclear about something, speak it up as soon as possible, because the gap will just grow. X of t equals cosine of t. Y of t equals sine of t. And let's take this over some particular range for this range of t. Okay, so I'm going to sketch it. What do you see here? What do you think this parametric curve is producing? Yeah, a circle. So when t is equal to 0, then we have cosine, it's just 1, sine is 0, right? So we're here, yeah? When t is equal to pi over 2, then cosine is 0, and then sine is equal to 1, right? So we know the graphs of cosine and sine, yeah? So this is cosine. Yeah, so this is pi over 2, 3 pi over 2. I'm going to overlay sine on top of it. So this is sine. These elementary graphs you've got to be familiar with at this point. This is sine right here. So we are here when t equals 0, right? So this is x of 0, y of 0, because cosine is equal to 1, sine is equal to 0. When at pi over 2, we have sine is equal to 1, cosine is equal to 0, so we're here at x of pi over 2, y of pi over 2. Yeah, when we're at pi, then now sine is equal to 0, yeah, but cosine is equal to -1, yeah. So now we're over here. So this is x of pi, y of pi, right here. And when we're at 3 pi over 2, like this, then cosine is equal to 0, and sine is equal to -1, right? So we're here. Y of pi over 2. Yeah, and if we put intermediate points in, we'll see that we go around like this. Like this, yeah? Cool. Okay. Or we could look at this thing right here, and we observe the following thing that we know. So we know that cosine squared plus sine squared is equal to 1, right? Start with cosine. So that's the same as saying that x of t squared plus y of t squared is equal to 1, yeah? Which means that every point x of t, y of t lives on the unit circle, yeah? Around 0. Right? Because this thing is exactly saying what's the distance of the vector x of t, y of t away from 0, right? This is saying that the hypotenuse of the triangle which goes like this to x of t, y of t, right? The hypotenuse is this x of t squared plus the y of t squared, square rooted, right? So the hypotenuse squared is this thing, it's equal to 1, so that's the same as saying that we live on the circle, yeah? All right, so what does our b do in this case? At time 0, it's here, right? And then it steadily goes round, 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 and then at time 2 pi, it's back where it started. It's back where we started, yeah? Cool. What if we considered this? What happens then? What does our b do then? Yeah, it's going to do another loop around the same circle. So we go 0, steadily around, 2 pi, and then we go around again. 2 pi, now we're at 3 pi, and here we're at 4 pi, yeah? So notice that this thing, this parametric curve of this range, goes around exactly the same set of points as when we considered from 0 to 2 pi. Yeah? But this thing's a different path. The b is doing a different thing. The b is doing a different thing. Yeah? Yeah? So the set of points is not the same as the path. Start again. The set of points is not the same as the journey of the b, right? It's not the same as the parametric curve. Set of points is where the parametric curve lives, but the parametric curve contains more information. Let me make another example. Suppose we do this. Suppose we have the same range of time, but now we do this. Okay? Tell me what this parametric curve does. So what's the journey of the b when it's given by this? Yeah, but tell me more. It traces the same circle. Well, we're going over the same range of time. So we're going from 0 to 2 pi. So what happens as we go over? So I see what you're saying, but we're considering the journey from 0 to 2 pi. So what does the b do? Perfect. It traces the circle twice, right? So x is a circle twice. Yeah? So if this is our curve, right, and we have another curve, which is just for my cosine of t, sine of t, if we draw them, they look exactly the same. Yeah, they look exactly the same, but they're completely different. Right? Then this guy, the b goes around 2 times the curve, yeah, in the same amount of time because it's flying twice the speed of the first b. Yeah? So again, the set of points where the path goes over is not the same as the path. We have the same set of points and a completely different path that gives it. And that's one of the things we have to get clear in our heads as we go forward with this. Yeah? Cool. All right, let's put this back where it was so that it's consistent with the picture I've drawn. Let's do this example. This is example 3. What about this? What about x of t is equal to sine of 2t y of t is cosine of 2t. And the range is t between 0 and 2 pi. Where does this thing start? And what does it do? First of all, where does it start? Oh, I didn't write the y. And what does it do? So where does it start, this guy? Yeah, starts at 0, 1. Starts up here this time. Yeah. And what is it? Where is it? As time increases from 0, where is it going to go? Which direction is it going to go? Look at the sine cosine graph. Show me with your finger where it starts to go. We are here, and then show me with your finger where it starts to go. All right, say it in words where it's going to go. Is it going to go clockwise or anti-clockwise? No, clockwise. This guy is going anti-clockwise, right? This guy is going anti-clockwise, going around like this. Yeah, this is anti-clockwise. Yeah. Whereas this guy, as t increases, right? So then as t increases, sine is going to decrease and cosine is going to increase. So it goes like this. So it's going in this direction. Yeah? It's going to go around like this. You see what I mean? Yeah? And same as before, this thing is going to go around more than once. It's going to go around 2 times. But now it's going in the opposite direction as before. Yeah? So this is yet another example of something which goes over the same set of points. It's still the unit circle, but it's doing it still differently. Okay? Cool. All right. Let's do this. This is example 4. Find the parametric equations. So parametric equations from now on are para equations of a circle of radius r centered on hk. All right. Think about how we did a circle before. Now we've got to do this except it's centered on h, k. How can we express the fact that a circle is centered on h, k? So these circles are all centered on 0. Yeah? How can we express the fact that we want it centered on h, k? What would the x of t be? What would the y of t be? Okay, which do you want to do? Add or subtract? Which one? Maybe you want to do both, but which do you want to do? Okay. Okay. Yes. So, and how do we deal with the fact we want radius r instead of radius 1? Come on, one of you. The full expression? Good. Great. So help me with this. So x of t, what shall I put here? X of t is equal to someone else. What's the y of t in that case? Excellent. Good job, people. Yeah, this would do it. However, it's a convention that we prefer to go anti-clockwise than clockwise. So later, as you learn more multivariable calculus, you will learn this that it's simply a convention that we'd like to go anti-clockwise around a closed curve, and just because that if we do the simplest parameterization of the curve, which is cosine of t, sine of t, this thing naturally goes anti-clockwise. So what you told me is exactly right. This thing will go around the circle, which is all that's required. But the solution standardly given is this. And it's exactly the same thing, except now I'm going anti-clockwise around this. Yeah? So let me reuse this picture. What this is the circle centered on this point, which is hk, okay, of radius r like this. Right? This is what this thing is. And then when t is equal to 0, we start here, and then we go around like this in an anti-clockwise way. Like this, like this, like this, like this, like this, like this, like this. So I teach a subject called complex analysis at graduate level, where we do a lot of integrating around curves. And one of the things that's very helpful is to always remember to go anti-clockwise. Because if you suddenly go clockwise, then your answer becomes different. All right, cool. Everybody happy? Yeah? Everybody happy? Excellent. All right, let's keep going. Tell me about this curve. X of t is sine of t, and y of t is equal to sine of t squared, like this. What set of points does this thing live on? What does the path do? Let's start with t equals 0 and then just go forward. So for t bigger than equal to 0, what does this thing look like? What does it do? Good. That's very good. So we know that it's trapped between -1 and 1 forever, exactly as this guy says, because that's what this thing is, right? So it's somewhere in this strip, yeah? That's good. Okay, what else do we know? Good. So now we have it trapped within this box, right? So this is 1. This is 1 here, and this is -1. Well, not box, but this rectangle. So it lives somewhere inside this rectangle. Yeah? Lives somewhere inside here. Okay. So our B is getting more and more restricted, but we actually want to know the path of the B. So what relationship do you see between the coordinates x of t and y of t? Y of t is always x of t squared. Okay. Now, I claim that gives us further restriction on what the path of the B has to be. Try and tell me what that further restriction is. Did you say that y of t is x of t squared? So what further restriction? Can the B be here at some point? No, right? Because y of t is x of t squared, and as I put x of t, it would have to be 0, so it can't possibly be here, right? Yeah? It's not here. So if we're stuck, then we can just start to put in points, right? So we can just start to put in points for various values of t. So when t equals 0, where are we? Oh, go ahead. Yes, that's something else we know. So that means, I mean, we are we are sort of slowly getting there by exclusion, right? So we can cut out this part because, as you say, the magnitude of y of t is less than the magnitude of x of t. So it can't be in any of this upper triangle here. Okay. So can't be here. But let's actually try and get the curve that it lives on. Let's try and get the curve. Come on. What relation did you tell me between x of t and y of t? Right. So the relation we see here is that y of t is equal to x of t squared for all t, right? Bigger than 0, let's say. Yeah? So what does that mean? Well, this means that x of t, y of t lives on the graph of y of x is equal to x squared. Yeah? Maybe I want to change my letters so that they don't overlap. So it lives on the graph. Let's write capital Y of x is equal to x squared, right? So the graph of capital Y of x equals x squared is exactly this graph, right? Didn't do a very good job. This is the danger when I do a bad diagram with too many colors, it all gets smudged. So like this, right? This is the graph of capital Y of x. Yeah? Yeah? And this thing has to live on this graph because we exactly have this relation, right? The thing in the red box, yeah? So every single x of t, y of t has to live on this graph. Has to live on this graph. Has to be some point on this graph, yeah? Okay, cool. And that knowledge gives us all the other stuff that we painfully got one step at a time, right? Yeah? All the other stuff we painfully got is now contained within the fact that this thing has to live on this graph and the fact that the x coordinates between -1 and 1, right? Yeah? So the part of the graph of this thing over -1 to 1 is exactly where all of these guys, x of t, y of t, have to be. That's where the b lives for all eternity, yeah? Flying up and down this graph. Yeah? So this relationship here gives what points this thing has to be on. Do we know that it goes on all the points of this graph over -1 to 1? Maybe it just lives on a little part of it. What do you think? Well, let's think, right? So what we have here is x of t is sine of ty of this thing. So y for sure will always be positive, right? Well, what about x of t? If we just look down at the x-coordinate of our b as time moves forward, what range will that be over? -1 to 1, right? -1 to 1. Yeah? Which means that if we're looking at the path of the b, then it has to be going throughout this entire range from -1 to 1, right? Yeah? So this thing is a different game. So you have to realign. You have to realign your thinking about graphs from R to this new situation. Yeah? And that sometimes is a bit of a jump because you're so used to thinking about things from R to R. But now it's a different thing. Now it's a different thing. All right. So we know that it has to go over the entire graph, right? because x of t is going to go from -1 to 1 forever, right? Yeah. And if we just look at what x of t does, I mean, it starts at 0, it's going to go upwards, hit 1, yeah, when we are at pi over 2, yeah, and then it's going to go back and it's going to hit 0 when we are at pi, then it's going to hit -1 when we are at 3 pi over 2, and then it's going to hit 0 again when we're at 2 pi, yeah? So that's what the x-coordinate does. It goes up, back, up, back. That's what the x-coordinate does forever, yeah? Yeah? Cool. All right. And what does the y-coordinate do? The y-coordinate is just the x-coordinate squared. So as the x-coordinate's going like this, the y-coordinate's going like this, right? Which it has to do because it lives on this path, right? So the B's motion is to start here and to go up, 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 go up, up like this, yeah? And then at pi over 2, it changes direction and goes down. So it goes up, goes up, goes up. And then it changes direction and goes down, 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 down through here, yeah? And here we are at 3 pi over 2, and then we go down again like this, yeah? So the B is going like this forever, yeah? Forever. Cool. All right. So that is how we start to be able to visualize, to sketch parametric curves. Okay. Where this is going next is we're going to start to try and do calculus with parametric curves. We're going to start to talk about what it means to have a derivative of a parametric curve, right? And then how can we use the information of derivatives to do things like sketch parametric curve better, to find the points on the parametric curve where the slope of the parametric curve is a particular thing, right? That is what we are next going to do. We're going to try and start to build a calculus of parametric curves. And what really is an excellent exercise for you people is to try and ask for yourself what the derivative of a parametric curve should be, right? So we know that the derivative of a function from r to r is just a slope. It's a number that gives this slope, right? Because the local information of the way this function behaves around here is just given by this slope, this one number, right? So f prime is a number, yeah? Now, if we have a parametric curve, okay, and we look at it at some small scale, think about what thing contains the local information of the way the parametric curve behaves around some particular point, say x of t, y of t. Think about what that thing could be. What is that object? Try and come up with an expression for it. Don't look in the book. Try and come up with it yourself. Try and come up with something that gives all the local information as you get very small around some particular point in time, x of t, at some particular point in time given by x of t, y of t. Let me say that better. Some particular point of time given by t where the coordinates are x of t, y of t. Okay? Think about that. Think about what the derivative can possibly be, and then we'll discuss it in the next class, and we'll build from there. All right, that's it for today. Stay if you have any questions. Otherwise, I'll see you all on Friday. Have a great day.